Hi everyone, welcome back to the last day of new material. Woohoo! Section 4.7. Yes, this is our last day of new material. The next 2 days we will be reviewing for the final exam. So be sure to come to the Zoom meetings for that. But you guys have made it to the end. Good job. Today's mathematician of the day is Dorothea Vaughn. She helped NASA in their quest to send man to the moon. She was NASA's first black manager and used mathematics to code many important calculations for NASA. She was featured in the movie Hidden Figures, which I definitely recommend. And did you know that Aztecs used the hand, heart, and arrow symbols as early as the 1300s in order to depict fractional distances in their land usage? Again, I am always just very thankful that we have numbers to symbolize numbers. So in order to wrap things up for this course, today we are going to be discussing something called L'Hopital's rule. And I'm not going to lie, I think it's strange that the textbook decides to put this particular theorem or rule in this section at the end of the term. But that's the way that it goes. So we are going to be studying this, and I think you're going to be like, Amanda, why didn't we learn this way at the beginning of the term? And my answer is, I don't know, I think you should have, but that's the way that the textbook has it, so that's the way that we're learning it. So here is what L'Hopital's rule says. Suppose f and g are differentiable on an open interval I containing the point A with g of x not equal to 0 on this interval when x is not equal to a. If we have that the limit as x approaches a of f and the limit as x approaches a is 0, then if we have both of those are equal to 0, then we have the following. The limit as x approaches a of f of x divided by g of x is equal to the limit as x approaches a of f prime of x divided by g prime of x. So if I get the limit as x approaches a is equal to 0 over 0, basically, then I can take the derivative of the top and take the derivative of the bottom. And if I still plug in x equals a and I get 0 over 0, I repeat this until we get a constant. So maybe I'll have to take 2 derivatives or 3 derivatives. Repeat this until we get a constant. Unless you can see that you will never get a constant. I want to note here that this is not the same thing as taking the derivative of f over g using the quotient rule, right? We are not using the quotient rule here in order to take the derivative of f over g. We are simply taking the derivative of the top and dividing it by the derivative of the bottom. So this is not the same as the quotient rule. So let's use L'Hopital's rule in order to evaluate the limit as x goes to 1 of x cubed plus x squared minus 2x divided by x minus 1. So first things first, I am going to plug in x equals 1 to see what happens. So when I plug in x equals 1, I get 1 cubed, which is 1, plus x squared, which is 1, minus 2 divided by 1 minus 1. This is clearly 0 over 0. So because when I plug this point in, I get 0 over 0, I need to use L'Hopital's rule. So I see that my top here, f of x is equal to x cubed plus x squared minus 2x. This gives me that f prime of x is equal to 3x squared plus 2x minus 2. And my bottom, g of x, is equal to x minus 1, which means that g prime of x is simply equal to 1. So L'Hopital's rule says that the limit as x approaches 1 of my original function, which was x cubed plus x squared minus 2x divided by x minus 1, this limit is equal to the limit as x approaches 1 of the derivative of the top, which we found to be 3x squared plus 2x minus 2, divided by the derivative of the bottom, which was 1. If I plug in x equals 1, I get 3 plus 2 minus 2 divided by 1, which is 3. So L'Hopital's rule eventually gave us a constant. We had to take only one derivative of the top and the bottom, and we got 3. So this is how we use L'Hopital's rule. Actually, I'd like for you to try number 2 on your own. So try number 2 by yourself and see if you can do this on your own, and then come back together and we'll do it together. All right, hopefully you've tried this on your own. First thing, right, we always check to see what actually happens if I plug in x equals 0. So we have the limit as x approaches 0 of e to the x minus 1 divided by x squared. So if I plug in x equals 0, I get e to the 0 minus 1 divided by 0 squared. Well, e to the 0 is 1, so I get 1 minus 1, which is 0, divided by 0. And of course, this tells me that I need to use L'Hopital's rule. So I see that the limit as x approaches 0 of e to the x minus 1 over x squared is equal to the limit as x approaches 0. I take the derivative of the top. Again, we're not using the quotient rule here. We're just taking the derivative of each part. The derivative of the top is equal to e to the x minus 1. The derivative of the bottom is equal to 2x. Okay, what happens now if I plug in 0? Well, on the top here, I get e to the 0 minus 1 divided by 2 times 0. So here I still get 0 over 0. That tells me that I need to apply L'Hopital's rule again. So I take another derivative of the top and the bottom. So I will get the limit as x approaches 0. The derivative of the top now is e to the x, and the derivative of the bottom is equal to 2. Now if I plug in 0, I get e to the 0 divided by 2, which is 1/2. So finally we get a constant. So here I had to apply L'Hopital's rule twice, but that is okay. I apply it as many times as I need to until we get a constant or positive or negative infinity. All right, so that was if the top and the bottom are both equal to 0 when I plug in my point. But we also have some other things that we can, hold on one second. Sorry about that. Okay, so we have some other rules for L'Hopital's rule where the top and the bottom will equal positive or negative infinity. They don't have to be the same kind of infinity, but if I get the top and the bottom are both equal to infinity, then I can use L'Hopital's rule also. So suppose f and g are differentiable on an open interval I, containing a point A with g, the bottom, not equal to 0 on I when x is not equal to a. If the limit as x goes to a of f and g are positive or negative infinity, then we can apply L'Hopital's rule. So this will be the limit as x goes to a if I have the top f and the bottom g and they both go to some kind of infinity. Then I do the same thing. I can take the derivative of the top and the derivative of the bottom to get f prime over g prime. And I repeat this as necessary until I get a constant. Get a constant. Unless I get positive or negative infinity, right? So if I were to get positive or negative infinity as my limit, that would mean that I would have the top, f or f prime or whatever, equals infinity, and the bottom is equal to a constant. So if I have f over g or f prime over g prime as infinity over infinity, this is it means nothing to us, right? This could equal a constant, this could equal 0, this could equal infinity. So that's why I have to take derivatives again and again until I either get a constant or until I get infinity over a constant, which is infinity. But the form infinity over infinity does not tell us anything about the limit. So let's try an example here. Let's take the limit as x goes to infinity of 4x cubed minus 6x squared plus 1 divided by 2x cubed minus 10x plus 3. So of course, if I plug in infinity here, I get infinity over infinity, right? That's pretty simple to see. So L'Hopital's rule tells me, since I have infinity over infinity, I can take the limit as x goes to infinity of the derivative of the top divided by the derivative of the bottom. So the derivative of the top here is 12x squared minus 12x. The derivative of the bottom is 6x squared minus 10x. Okay, well if I plug in x equals infinity here, I still get infinity over infinity. So I need to take the derivative again. Whoops, sorry about that. So when I take the derivative again, I get 24x minus 12 divided by 12x minus 10. If I plug in x equals infinity, I still get infinity over infinity. So I take the derivative again, I get limit as x goes to infinity of 24 divided by 12, which is just 2. So in this case, I had to take a bunch of derivatives, but I did eventually get a constant. If you remember back in your good old days of college algebra, we could have also done this in a slightly different way by taking a look at the leading term on the top, which was 4x cubed, and the leading term on the bottom, which was also, it was 2x cubed. Since I'm wanting to find the end behavior, the limit as x goes to infinity, I could have just looked at the 4x cubed divided by the 2x cubed. Since I have the same exponent here, my end behavior is simply the ratio of the leading term, the leading coefficient of the top divided by the leading coefficient of the bottom, which is 2. So this is just another way to get to that point, right? Get to the same point of the ratio of the leading coefficient of the top and the leading coefficient of the bottom. But we do get there using calculus. Yay, calculus. Alright, so far we have just seen that L'Hopital's rule applies when I have 0 over 0 or infinity over infinity. But what if I get something else, like infinity over 0 or 0 divided by infinity? We call these indeterminate forms. And we have to algebraically manipulate my function in order to get my form as 0 over 0 or infinity over infinity. So we're going to do some examples here where we algebraically manipulate some functions. So first I have that I want to evaluate the limit as x goes to infinity of x squared times sine of 1 divided by 4x squared. So if I were to plug in x equals infinity here, I would get x squared is equal to infinity, and then I would get sine of 1 over infinity, which I would define to be 0, so sine of 0, and sine of 0 is 0. So I get infinity times 0, and this does not allow me to use L'Hopital's rule yet, but I need to get there, right? I can get to a point where I can use L'Hopital's rule. So how I am going to do this is I'm going to take this x squared and I'm going to divide this whole function by the reciprocal of x squared. So remember, x squared is the same thing as 1 divided by 1 divided by x squared. So this is the trick that we are using. I'm going to rewrite x squared as 1 divided by 1 divided by x squared. So we will divide by reciprocal of x squared. So I will get the limit as x approaches infinity of sine of 1 divided by 4x squared divided by 1 over x squared. So now that I have done this, let's see what happens if I plug in x equals infinity. On the top, I will get sine of 0, which is 0. If I plug in infinity into the bottom, I get 1 divided by infinity, which I have defined to be 0. So now, if I plug in x equals infinity, I get 0 over 0, which is what I need in order to apply L'Hopital's rule. So now I can use L'Hopital's rule. So I need to take the derivative of the top and the derivative of the bottom. In order to take the derivative of the top, I'm going to have to use the chain rule. So let's do this off to the side here. So I have sine of 1 divided by 4x squared. That means that my outer function will be sine of x. My inner function will be 1 divided by 4x squared, also known as 1/4 x to the negative 2. That gives me g prime is equal to cosine of x, and g prime is equal to negative 1 divided by 2 x to the power of negative 3. So the derivative of the top here is limit as x goes to infinity. F prime of g, that gives me cosine of 1/4 x to the negative 2 times g prime, which is negative 1/2 x to the negative 3, divided by the derivative of the bottom. What is the derivative of the bottom? Well, remember that 1 divided by x squared is the same thing as x to the power of negative 2. So if I use the power rule here, I will get that this derivative is equal to negative 2 times x to the power of negative 3. Okay, so this is what I have so far. The derivative of the top divided by the derivative of the bottom. And I can cancel some things out here. So I'm multiplying here on the top, I am multiplying this cosine function by negative 1/2 x to the power of negative 3. Since I'm multiplying those two functions together, I can cancel the x to the negative 3 from the top and this x to the negative 3 on the bottom. I can also cancel out this negative and this negative. So this will give me the limit as x goes to infinity of 1/2 cosine 1/4 x to the negative 2 divided by 2. And now if I plug in infinity, what do I get? Well, if I plug in infinity into 1/4 x to the negative 2, I get 0. So what is cosine of 0? It is equal to 1. So I get 1 times 1/2, which is just 1/2, divided by 2, and this is equal to 1/4. So here the trick was, since I had infinity times 0, I needed to divide by the reciprocal of x squared. And if I have this kind of function, I will always divide by the reciprocal of whatever I have in front. So if I have an x to the power of 2, I'll divide by the reciprocal of that. If I have an x to the power of 7, I'll divide by the reciprocal of that. That is kind of our trick here. So once I divided by the reciprocal, I was able to use L'Hopital's rule. Then I had to use the chain rule in order to find the derivative, but we know how to do that, so no problem there. And then I finally got a constant. So pretty cool, huh? All right, let's do one more example with this. We want to evaluate the limit as x goes to infinity of x minus the square root of x squared minus 3x. So if I plug in x equals infinity, I get infinity minus the square root of infinity, which we define to be infinity. So this is equal to infinity minus infinity. And we don't know how to use L'Hopital's rule with that, right? This is not one of our forms 0 over 0 or infinity over infinity. So this is what I am going to do. I'm going to factor out that x squared from the inside of my square root. So I will get this limit as x approaches infinity, x minus square root of x squared. When I factor out that x squared from both terms, I will get 1 minus 3x divided by x squared gives me 3 divided by x. Okay, so now I have two things that are being multiplied inside my square root, right? And when I have two things that are multiplied inside my square root, I can take one of them out of the square root if I want to. So that's what I'm going to do. I'm going to take that x squared outside of the square root. We know that the square root of x squared is just x. So this will be equal to the limit as x approaches infinity of x minus x times the square root of 1 minus 3 over x. So here I have just taken that x squared out of the square root so that I have x. And now from both of these terms, x and x times square root of 1 minus 3 over x, I can factor out an x. So this is limit as x goes to infinity of x times 1 minus the square root of 1 minus 3 over x. So here I have just factored out an x from both terms. So let's check out now what happens if I plug in x equals infinity. Well, if I plug in x equals infinity, I get infinity times 0. This is what we got in the previous example. So when I get infinity times 0, I need to divide by the reciprocal of whatever x I have. Right here I just have x to the power of 1. So I'm going to divide by the reciprocal of x, since I have that term infinity times 0. Divide by reciprocal of x. So this gives me the limit as x goes to infinity of 1 minus the square root of 1 minus 3 over x divided by 1 divided by x. I am dividing by the reciprocal of x. And now if I plug in x equals infinity, on the top I get 0 and on the bottom I get 0. So finally I have 0 over 0 and I can finally use L'Hopital's rule. So this is 0 over 0. Now according to L'Hopital's rule, I can take the derivative of the top and divide it by the derivative of the bottom. So what will the derivative of the top be? Well, I have to use the chain rule here. So my outer function f will be square root of x, which means f prime is equal to 1 over 2 root x. And then my inner function g is 1 minus 3 over x, also known as 1 minus 3 times x to the negative 1. This makes g prime equal to 3x to the negative 2, or 3 divided by x squared. Okay, so here I get that the derivative of the top, limit as x goes to infinity, of course that 1 just disappears, so I have negative, since I have that negative in front of the square root, f prime of g, that is 1 divided by 2 square root 1 minus 3 over x, times g prime, which is 3 divided by x squared, divided by the derivative of the bottom. And the derivative of the bottom here is negative 1 divided by x squared. Okay, now let's take a look. Can I cancel anything out? Well, I can. I have a 3 over x squared here on the top and a negative 1 divided by x squared on the bottom. So first I'm going to cancel this negative with this negative. And if I cancel this 1 over x squared with this 3 over x squared, I'll still be left with that constant 3 on the top. So I'll have the limit as x goes to infinity of 3 over 2 square root 1 minus 3 divided by x. Now if I plug in infinity here, on the inside of that square root I get 1 minus 3 divided by infinity, and 3 divided by infinity is just 0, right? So I get 1 minus 0 underneath the square root. So this gives me I have 3 divided by 2 times the square root of 1, which is just 3/2. Ooh, so this one was a little bit tricky because I had to do several things before I could use L'Hopital's rule. So since I had that x squared underneath my square root, I factored it out underneath the square root. Then I factored out that x squared from the square root. Then I had to factor out an x from both of those terms. Then I had my indeterminate form of 0 times infinity, and when I have that term, I need to divide by the reciprocal of whatever x I have. So in this case, I divided it by the reciprocal of x, so I divided it by 1 over x. Then I had a form where I can use L'Hopital's rule, 0 over 0. And then from there, I just took the derivative as usual, and eventually I did get a constant. All right, so we do have a procedure for when we have these kind of indeterminate forms, when I have to manipulate my function to get it into 0 over 0 or infinity over infinity. So here's my procedure. When I have a function like 1 to the power of infinity, 0 to the power of 0, or infinity to the power of 0, this is what I do. So these forms are a little bit different than the ones in example 4 and 5, but they are also indeterminate forms. So here is what I do. I assume that the limit as x goes to a of f of x to the power of g of x has the indeterminate form 1 to the power of infinity, 0 to the power of 0, or infinity to the power of 0. In order to use L'Hopital's rule for this, I first need to analyze L equals the limit as x goes to a of g of x times the natural log of f of x. So basically I use natural logs in order to get that g of x down to the bottom. And then this can be manipulated to get 0 over 0 or infinity over infinity. Okay, and then when this limit right here, the limit as x goes to a of g of x times natural log of f of x, when L is finite, not infinity, because I basically had to take the natural log in order to get that g of x to the front, the limit as x goes to a of f of x to the power of g of x is equal to e to the power of L. Otherwise, if L is not finite, then I just plug in whatever L is into e to the power of L, and it will either be 0 or infinity. So the reason that I have to do this second step is, again, because in order to get that g of x down to the bottom in front of f of x, I have to take the natural log of it. And in order to undo that natural log, once I get that L, I have to exponentiate it so that I balance everything out. So let's use this procedure in order to evaluate the limit as x goes to 0 from the right of x to the power of x. So here I have the limit as x goes to 0, so I have the form here, 0 to the power of 0. This is one of the forms that I've just learned about in this procedure. So my first step is I need to analyze L, which is equal to limit as x goes to 0 from the right of g of x. That is the x in the exponent. So that is x times natural log of this x, the bottom x. Okay, well, what is the form of this? Well, that x will just give me 0, and the natural log of 0 from the right is infinity. So this is equal to 0 times infinity. We know what to do here, right? Now that I have 0 times infinity, I need to divide by the reciprocal of that x. So I divide by reciprocal of x. That gives me the limit as x approaches 0 from the right of natural log of x divided by 1 over x. So what do I have here? On the top I have infinity, and on the bottom I have 1 over 0, which I define to be infinity. So I have infinity over infinity, so now I can use L'Hopital's rule. So here on the top, what is the derivative of this? Natural log of x. The derivative of natural log of x is equal to 1 divided by x. And the derivative of the bottom here will be negative 1 divided by x squared. I don't have a constant yet, right? If I plug in x equals 0 from the right, I still get infinity over infinity. But here's what I'm going to do. In order to get rid of that dividing by x squared on the bottom, I'm going to multiply the top and the bottom of this fraction by negative x squared divided by negative x squared. That will cancel out the negative 1 divided by x squared on the bottom, and I will be left with the limit as x goes to 0 from the right of negative x, because I have negative x squared times 1 over x. And this is just equal to 0. So this limit is equal to 0, right? Limit as x goes to 0 of negative x is 0. So this is my L, right? I just solved for L. So this is not the limit of my actual function, because my second step, since I just basically took the natural log of this function, I need to exponentiate it. So the limit as x goes to 0 from the right of x to the power of x is equal to e to whatever I just found for L, which was 0. And e to the power of 0 is equal to 1. So we did have to use our trick of dividing by the reciprocal of x here, but the other trick that we used in this example was to take the natural log of the function so that we can get my top power down to the bottom, and then eventually use L'Hopital's rule. So yeah, there are a lot of different forms of L'Hopital's rules in this section. I hope that I gave you a good sample of the different kinds of forms that you'll see. Otherwise, Pearson gives you a lot of practice with these kinds of problems, so I do recommend definitely doing a bunch of those problems for practice. Let me know if you have any questions. I would love to see you at our Zoom meeting. Otherwise, good luck studying for the final exam. Let me know if you have any questions. I'll see you later.